Is everyone ready for more scintillating math content? So, we're going to get to one of the most celebrated results in statistics. Yay! Probability of A and B equals probability of A given B times probability of B equals probability of B given A times probability of A. We all talked about this the last 30 seconds before we took the break. That all seems totally reasonable. Everyone on board with this? I'm going to do something amazing. Probability of A given B equals probability of B given A times probability of A divided by probability of B. This is Bayes' theorem. I'm not sure why it's a theorem. It's sort of from the definition. Nevertheless, this is the root of all Bayesian statistics. It enables us to think about changing the direction of the conditional probability. Why would we care about changing the direction of the conditional probability? I'm going to give you a good example of why we should care from something that maybe one of you will propose to do for a thesis proposal, and if your committee is diligent, they'll make you do this math and think about it, and think about what it means. Let's say that you have an ELISA assay for apoptosis. You've got cells in a little dish, and when they give up the ghost and fall on their little cell swords, the little well turns bright blue, and you can read that out on a plate reader. And you have an interesting cancer line, some sort of human primary cancer line that you would like to find a drug that causes those little cells to fall on their little cell swords. So this is called a drug screen. It's a mainstay pharmacology and biology and drug development. So let's further posit that this ELISA assay that you have is pretty good. So let's say it's 99% sensitive. So this is the true positive rate. So that means if you put positive control compound that you know makes your cells die on 100 different wells of cells, 99 out of those 100 are going to turn blue. And it's really hard to get a sensitive assay that's also specific. But let's say it's really specific. So it's 95. So specific is the true negative rate. If you put vehicle control, just DMSO or just water, on 100 cells, 100 wells of cells, only 5% of them will turn blue. So 95 out of 100 true negatives will register as negative. And the reason that these are hard to deal with, hard to get both at the same time, is if you want a really sensitive test, maybe you crank up the sensitivity, you crank up the gain on the amplifier so that any tiny little bit of blue, you say, yes, those cells are dead. But if you do that, if you crank up the volume all the way, you're going to be vulnerable to noise. And so sensitivity trades off against specificity almost always. So here we've got a really sensitive test that's 95% specific. So this seems like a great test to go do our drug screen. So let's figure out what that actually means. Okay, so we're going to build a little 2x2 table. You're probably getting sick of little tables, but this is statistics. So we've got truth that the compound is active or inactive. And then we've got the assay that gives you a positive result, blue, or a negative result. So 99% sensitive means that if the compound is really active, we'll get 99, and 1. 95% specific means that if the compound is truly inactive, we'll get 95 and 5. Okay, so we can ask from this, what is the probability that the test is positive given the drug is active? Well, that's our sensitivity. You know, we calibrated that in the lab with our positive control and our negative control. But in the real world, we don't know that the drug is active. We know that we got blue. So what we really want to know, what's the probability that some random compound synthesized by ants in a South American rainforest is active given that our wells turn blue? This is the thing we want to know. This determines whether our screen is going to work or not. So how do we calculate that? Oh, if only this board went up. All right, so let us use Bayes' theorem to calculate this probability. Probability of active given positive equals probability of positive given active, we know that, times probability of active, times probability of positive, so this is not immediately helpful, but we can start to ask about, okay, well, what's the probability in our library of compounds that a drug is going to be active? Let's say we've got a fantastic library of compounds. We've got 5,000 compounds. And we think that these compounds are so great that 20 of them are going to have this activity that we need to kill this cancer. 20 out of 5,000. 0.4%. That's a guess. It's an optimistic guess, but that's our guess as to probability that a given random drug is going to be active. All right, so now how do we figure out the probability that the test is positive? All right, I'm going to do some sort of silly seeming things. So the probability that the test is positive is probability that the test is positive and the compound was active plus probability test is positive so right, either the compound can be active or it can be inactive. So we can just add these together. There's no overlap between active and inactive. And now we should be able to use our other rules to simplify this into pieces that we know. So what's our rule for probability of A and B? We've got two rules now. One rule is that we multiply them. Does that seem like a good rule to apply here? No, because there's probably some relationship between a test positive and the compound being active. So what's the other rule? Okay, I'm just going to start writing an A and an I, because, again, lazy. Okay, does everyone buy this? That the whole world can be broken up, the whole world of positives can be broken into the probability that you're positive given that the drug was active, times the chances that the drug is active, plus the probability of a positive test given that the drug is inactive, times how likely the drug is inactive. This is the same thing we did. What's the fraction of the pie that, what fraction of the pie, when we're only looking at this one slice, where we've got 99 and 1, and 95 and 5, and then what fraction of the whole pie is this one particular slice? We've got active and inactive. Does that make sense? Everyone feel me? All right. Let's plug in some numbers, shall we? So, probability of active given a positive test is probability of positive given that the compound is active, that's 0.99, times the probability that a compound is active, 0.004. And then divide that by this same half again. Plus the probability that the compound is, that the test is positive given that the compound is inactive. So what's this probability? 1 minus the specificity, which is 5%. Again, this is a pretty good assay. 5% of the time it's a false positive, 99% of the time it's a true positive. This is a great assay. So let's time, 5% times the probability that the compound is inactive, which is a lot. That's 4,980 out of 5,000. Just draw that up, right? All right, so for those playing at home, what is our final probability that a drug is active given that we have a positive result? %7.3%. All right, so what's the probability of getting a positive result? We calculated it here. So that's 0.99 times 0.004 plus 0.005. Let me do that on my phone. I forgot to calculate that out in advance. 0.99 times plus 0.05 times 0.196. Oh, well, I did that wrong. Let's try it again. Okay, so the probability of getting a positive result is about 5.3%. Not too bad, right? 5.3% of 5,000 compounds. That's 265 compounds that are positive. Of those, 7.3% are going to be the ones you want. That's a lot of follow-up work, because now you can't do your assay. You actually have to get on a microscope and look at the cells are dying and stain them for all kinds of apoptosis markers. So it turns out that the background probability really matters, and that even a slightly crummy test totally kills you when you're looking for rare events. And we can figure this all out because of Bayes' law. Another simple way to think about this is, this table is wrong, right? Like we have 99 wells, or we have 100 wells of active compound and 100 wells of inactive compound. Really, what we think is that that the inactive compound is 250 times more likely than the active compound. So we need to multiply the inactive column times 250. I think I did that right. So now we can see that in the wild, for this one little corner of the table that we want, the 99 compounds that are going to be active, we're going to have to deal with 1,250 that are just wrong. So let's make sure that it's 99 plus 1250. 1349, 99 divided by 1349 is 0.73%. So again, we get the same 7.3% chance. So here's sort of a mathematical derivation for thinking about conditional probabilities, switching them around and understanding the application of biology. And here's a very intuitive way of thinking about the same thing. But in the real world, we don't have control compounds and active compounds in equal proportion. And once we adjust the proportions for what the real world looks like, our test stops looking nearly so rosy. All right. Now, in the last couple minutes, I want to talk about one last party trick that's really important for thinking about probability. And that is, how many worms do you, as the lazy graduate student, have to pick to have an acceptable probability of finding the homozygote? Now I say lazy because no one likes to set up the cross again, and if you don't pick enough worms, some of them aren't going to be the ones that you want. So how do we tell if a worm is DAF2 negative, GFP positive, homozygous? Well, it's green, but that only tells us if it's got one or more copies of GFP. So you have to put a single worm on the plate, let it lay some eggs that were self-fertilized, and see if all of those eggs were green. That will tell us if it was homozygous for GFP. Telling if it's homozygous for DAF2, that's actually more awkward. The easiest might actually be sequencing the gene to see if there's the single nucleotide polymorphism that changes this particular DAF2 loss of functional allele. That's a real pain. You've got to pick your worm off into a PCR tube, PCR out the region, send it out for sequence. Okay, this is a pain to verify a worm. So we're going to have to pick some random number of worms, and put them on individual plates and do this annoying assay. We want to do as few annoying assays as possible because we are all fundamentally lazy. But we also don't want to do too few assays, so we have to go back and set up this whole cross again from the beginning, because that's even more annoying. So, being good biologists, we say an acceptable probability of failure is 5%. We will not accept a probability of failure less than 5%. So we want to know how many worm plates do I need to pick to get my probability of success up above 95%. All right, so let's work it out. Starting from one worm plate. And we're going to do this picking the green worms, because, that makes it easier. So we have one plate, 1 out of 12. Probability of success. Is that above 95%? No. So obviously we need more plates. What is the probability of success if we have 2 plates? Plate 1 has a 1/12 chance of success. Plate 2 has a 1/12 chance of success. What's the chance of success on both plates? Is it 1/12 plus 1/12? Why not? Because if we did more than 12 plates, we would have more than 100% chance of success. That can't be right. So maybe the problem is how I'm speaking. What do I mean by success?
If you got one success, there's no
Yeah,
success.
we need at least one to be successful. So really with 2 plates, there are 4 possible outcomes. We could have yes and yes on the first one, and on the second one we could find a green worm on, the right worm on both. We could have yes and no, no, and yes, and no, no, and no. So there's 4 possible outcomes. What's the probability of this outcome?
Total 144.
Yep. 1, 12 squared. What's the probability of this one? Yeah, so that's 1/12 times 11th 12ths, so yeah. Okay, so what's the probability that we got what we wanted? Well, any of these 3 options are good enough for us, right? So it's this plus this plus this. There's another way to ask that with the mechanics that we built ourselves throughout class today. Probability yes 1 or yes 2. So what's that? What's our simple formula? Does everyone believe this? This seems reasonable? Okay, so that's 1 out of 12 plus 1 out of 12. And then we subtract 1 out of 144. So we can figure out what our probability of success is. And we can calculate that. Is that better than 95%? Okay, so what if we add a 3rd plate? Okay, so this was 1/12 plus 1/12 minus 12 squared. So that's probability of y1 or y2. And then we can just apply our rule again, right? And get the probability of y1 or y2 or y3, which is this thing plus this thing minus this thing and this thing Does everyone believe that this formula is a straightforward application of this basic rule to the case of 3? If you don't believe me, you can work it out. So, this is already looking awful, right? And now what if I told you that I want you to come up with a function as a function of the number of plates that gives you this probability? I couldn't even figure out a way to write that in closed form. It probably has to do with Pascal's triangle. It's confusing. So is there a better way? Is there a clever trick that we can all leave this room feeling enlightened that we have learned one clever trick to save us a lot of effort should we ever breed worms, or anything else where we need to care about a successive cumulative probability of successes. So we said that success is any of these options. What's the opposite of success? How many ways are there to fail totally? Only one way. How many ways are there to fail totally with 3 plates? Still just one. So, probability of failure given n plates is probability of failure with 1 plate. And then what do? Where do we put n? Multiplied by n? I heard something?
Exponent.
Exponent, there we go. Yes, raised to the n. Probability of failure 1 times probability of failure 2 times probability of failure 3. They're all the same. Raise them to the nth power. So, we can write probability of our overall failure equals, actually, let's just call it F, our single plate failure probability, which is 11 out of 12 times we're going to fail. Not great. F to the n. So now we want P failure to be less than 5%, right? We want to reduce our chance of failing to less than 5%. So F to the n is less than 0.05. What do we do? How do we solve? Logarithms? Logarithms. N log f is less than or equal to log 0.05. N, now log f. F is less than 1 because it's a probability. So what happens when you divide by things that are less than 1 with an inequality? Remember 5th grade, 7th grade? We change the direction. All right, now if you plug in 11 out of 12 and 0.05, we get n is greater than 34.4. So we're going to have to do 35 plates in order to make sure that we don't have to set up the experiment all over again. That's a lot of plates. But at least now we know. Would you have guessed that we would have had to do 35 plates? More? Fewer? I should have taken a poll. Next time I'll take a poll. So part of the homework for this week will be coming up with a better worm breeding strategy and figuring out how many plates you're going to need to use with the better worm breeding strategy. Application of simple statistical tricks to make your life easier in lab. I'll see you guys next week. Don't hesitate to email, post a message.